afternoon and good day everyone. I am Ali from Faculty of Electrical Engineering Technology, University Malaysia. Today, I would like to present my research about UHF sensor for online partial discharge detection on power transformer, Hilbert Fractal, Fractal, and Peano Fractal. For the today outline, I will start with introduction, design of the antenna, Fractal antenna, Hilbert Fractal antenna, Peano Fractal antenna, result and analysis, which is process of fractal loss, VSWR, radiation pattern, and finally the conclusion. Three types of antenna that I propose in the research, which are Hilbert Fractal antenna, Fractal antenna, and Peano Fractal antenna. All of these antenna are designed and simulated using CST Studio Suite software. I will go for the antenna design one by one. Several design of the fractal curve antenna which is specified must be considered to meet criteria of size for antenna installation in power transformer and also increase the gain and sensitivity of the sensor. The parameter of the antenna are determined as the outer dimension 10 times 10 cm. This dimension is chosen based on the antenna installation at transformer drain valve, which is 20 to 25 cm. These antenna are patch type antenna and contain 3 layers, which are patch conductor from copper at the upper layer, FR4 deposit substrate at middle layer, and ground layer from copper at the bottom layer. Next is the design of the Hilbert Fractal antenna. Hilbert Fractal antenna is one of the UHF methods that widely used to detect PD signal. Hilbert curve has an advantage in specifying the long length of the wire in minimum size of the antenna. Figure 2 shows the number of orders from first to fourth order for the Hilbert Fractal antenna. This is the basic equation for the Hilbert Fractal antenna to calculate the length of each line segment D and find the total length of the line segment S. The purpose of the Hilbert Fractal antenna is designed with a side dimension of 10 times 10 cm as shown in figure 3. For the proposed design, I use the fourth order of Hilbert Fractal. Now I show the design of the Fractal antenna. A Fractal curve is a type of Hilbert curve and also belongs to the fractal curve is specified type. The difference between Hilbert and curve is the arrangement of the curve and the end point of the curve. For the Hilbert curve, the starting and end of the curve are in opposite of the corner, while in curve, the sides are opposite. The fractal curve in 2 to 4 order are shown in figure 4. And figure 5 shows the design purpose for the 4th order fractal antenna. The equation of fractal antenna is same with the Hilbert Fractal antenna. Lastly, this is the design of the Peano Fractal antenna. The design of the Peano Fractal antenna is based on Peano Fractal curve, which have infinite order to fill up all the space. Figure 6 shows the composition of the Peano curve geometry from the first, second, and third order. For a Peano antenna, the length of each line segment D and the sum of all the line segment S are calculated by using the equation. Figure 7 shows the design of third order Peano Fractal antenna with a side dimension of 10 times 10 cm using the CFT software. Next, this is the result of fractal loss. What is fractal loss? Fractal loss is the parameter, also known as F11 parameter, represent the performance characteristic of the antenna and the power that reflects from the antenna. The fractal loss value should be less than negative 10 dB. Thus, the expected result for this research is the fractal loss of the antenna to fall in between 0.3 to 3 GHz. The lower the value of the return loss, the higher the efficiency of the antenna. Next is the result for S parameter. The first graph shows the result of S parameter versus the frequency of the more fractal antenna. It represents that there are 40 numbers of frequency band at which antenna can operate with the lowest return loss is negative 59.45 dB at a frequency of 2.25 GHz. However, the minimum frequency that this antenna operates is at 1.08 GHz, which is quite far from 0.3 GHz. The second graph shows the minimum return loss of Hilbert antenna is about negative 36.2 dB at 1.6743 GHz at the resonant frequency. It shows that there are 12 resonant frequency with the minimum frequency at 0.72 GHz with negative 15.15 dB return loss, while the maximum resonant frequency is at 2.77 GHz with negative 70.48 dB, which is near to UHF frequency for PD detection. The return loss graph in last graph show that the Peano antenna resonate at two resonant frequency, 1.51 GHz and 1.94 GHz only. The return loss value transmitted by the antenna at two resonance can be seen to be negative 70.77 dB and negative 20.8 dB respectively. The frequency range is slightly small, which corresponds from 1.51 to 1.94 GHz. Here we see the comparison of these three proposed antenna. As we can see, Hilbert Fractal is the best in terms of return loss and working frequency. Next is the VSWR value. VSWR is referred to voltage steady wave ratio, and it is a function of the reflection coefficient, which defines the power reflected from the antenna. The antenna with VSWR closer to 1 is better, which means the coefficient of reflection is 0 and no power reflected. In general, it is impossible to make the value of VSWR in 1 after fabricating the antenna. In order to fabricate the antenna, it is permissible to make the value of VSWR at the resonant frequency is less than 2. If the value is less than 5, it can still fabricate, but it is very vulnerable. While if the VSWR more than 5, it can be concluded that the antenna is unable to fabricate it. This is important to consider the low VSWR because of the high VSWR cause the power is very lost, and the reflected power can cause difficulties such as heating cables may have occurred. From first paragraph, it is found that the resonant frequency at 2.25 GHz is the 1.02 of VSWR value, which is near to 1. The second graph shows the VSWR for Hilbert Fractal antenna. The VSWR value at resonant frequency 1.67 GHz is 1.03, which is close to 1, while the VSWR value at other resonant frequency are 5, which is possible to fabricate the antenna. The VSWR graph in the last graph shows that Peano antenna VSWR value is 1.20 at 1.95 GHz resonant frequency, while the VSWR value is not consistent for other resonant frequency. Here is the comparison of VSWR value for three types of proposed antenna. It is clearly shown that the Hilbert Fractal antenna has the best performance with the smallest VSWR value, which is VSWR under 5 for the resonant frequency range from 0.8 to 3 GHz. Next is radiation pattern result. The radiation pattern result represent the coverage area of the power supply to the antenna in two-dimensional 2D or three-dimensional 3D graph. Omnidirectional radiation pattern is suitable to detect PD because it has a wide range of direction to detect the PD signal. The figure below shows the omnidirectional radiation pattern for 2D and 3D graph. Next, this is three different 2D radiation pattern for Moore fractal that illustrate the resonant frequency at 0.3, 1.65 and 3 GHz. Only at 0.3 GHz show that the radiation pattern in omnidirection. For Hilbert Fractal, the radiation pattern is daily hemisphere shape, which is omnidirectional when the frequency at 0.3 GHz and 1.65 GHz. The result demonstrates that the radiation pattern for these two frequencies are relatively stable. Next is radiation pattern for Peano fractal. It is clearly shown that the radiation pattern of this antenna is not good at 1.65 and 3 MHz. Lastly, we came up with this conclusion. Several types of fractal curve antenna which are more Hilbert and Peano have been selected and designed using ST Studio software with the dimension fixed at 10 times 10 cm. The result for all the antenna show all of these antenna are suitable for the partial discharge detection. However, the Hilbert Fractal antenna show the great performance in terms of return loss, VSWR, and radiation pattern compared to Moore and Peano Fractal antenna. That's all. Thank you so much for listening and have a good day.